Hello, everyone. We are the small scale track team. As you can see, our group's fairly large, so our presentation might take up a little bit more time. So first off, I would like to start with introduction and responsibilities. We had this at the beginning, so that way you get an idea of what we're going to be talking about later in the slides or throughout the presentation. So my name is Henry Z. I'm the team manager, and I will be also working with developing location and communication systems for the small scale team and designing different systems.
And I'm David, and I'm the track team lead. I'm responsible for organizing the track team and making sure we're going on the right direction. And I'm also in charge for track modularization, scheduling, and getting familiar with mapping programs such as SketchUp.
I'm Kenny, and I'll be our team's treasurer as well as the club's treasurer. I will be assisting in track design and managing the CAD drawings specific to the track team.
I'm Ali. I will be responsible for research, design, materials manager, and responsible for the mapping programs.
I'm David. I'm the team lead for the cart and the Bogey small scale. Basically anything to do with the small scale Bogey cabin is going to be what I'm looking at.
I'm Brian Hall, and I'm responsible for researching and developing the Bogey design we have.
Hi, my name is Nazar Hidari. I'm the lead for the control team of small scale. I'm responsible for research and development of the control system and position system.
I'm Thomas. I'm part of the controls team for the Bogey, and I'm working on the communication between multiple carts to the main hub.
I'm Kenny, and I'm also part of the controls team, and my responsibility is researching and developing a collision detection system.
All right. So as I said, we have a fairly large team, so we divided ourselves into 3 subgroups. We have like a track team, a pod team, and a controls team. So, and up to the track team.
So I'm going to be talking about the track, and here is our model of the current track. It has 3 wayside stations, and it's comprised of entirely of aluminum. It's supported by aluminum rods, and the aluminum rods are connected with the concrete slabs. There's a lot of problems with the track right now. One of the biggest problems is transportation. Each of the concrete pads that the track is using as support weighs about 35 pounds each. So lifting around 8 or 9 of them, you get tired. And another problem is assembly. One of the biggest problems is making sure the track is level. It took about maybe 6 of us, maybe half an hour, just to try to get the track a little bit level, but still it wasn't that perfect. Also, the track splits up into 5 main pieces. Each side of the rectangle is a piece with the diagonal as a 5th piece. And each of those pieces are comprised of maybe 10 to 15 smaller pieces which are screwed in. And when you assemble the track, when you take the track to the field and you assemble it, some of the screws get loose. And when you put the Bogey on it, the Bogey gets stuck on it. And one thing we're going to do is get rid of the diagonal track, because as you see, this is a map of downtown San Jose, and downtown San Jose is comprised of a grid format. So if you do put a diagonal track, it doesn't make sense because the diagonal track would be going through businesses, people's apartments, and things like that. So it doesn't really make sense to have a diagonal track. And then David's going to be talking about the solutions to the problems.
Okay, so after preparing for the EV rally, we spent most of our time reviewing and discussing new track improvement ideas from Mr. Gustafsson and the summer team. So we decided to implement their ideas of having a double track section which will allow for both directions. This is the double track section right here. There could also be a possible U-turn at the end of the double track section. And the new design will have additional stations both inside or outside the track loops. And we will also plan to build and test for elevation changes no larger than 17 degrees and also make the track more modular. So by implementing these features, we will reach our goal of creating a more realistic network. And as I mentioned before, Mr. Gustafsson would like to see a U-turn in our design. After discussing with the team, many problems came up when coming up with the design, and this is one of the more challenging aspects of our project. And before we get into details of our design, we will try to test how small a radius the bogies can handle first. And the picture on the farthest right is the current support structure on CAD drawing. And the square hollow tube right now, we have that, and it will replace the current aluminum rod. And if we zoom in at the support base, this is the zoomed in version, you'll see that we'll have angled brackets which will be bolted or welded in together with the tube. And instead of using the concrete bases, which are very heavy, we think a plate would be a much better solution, which will be welded at the bottom of the angle brackets. Now Kenny will talk about track modelization and elevation changes.
So we plan to design the track out of longer segments of aluminum. This will cause the bogie to travel more smoothly with less interruptions as caused by the current joints. I have talked with Mr. Muntz about the shop guru at San Jose State about bending aluminum flats, and he gave me reassurance that we could bend our own. One of the options he told me about is the Hausfeld bender. It might be challenging to become proficient, but instead of purchasing these pieces individually for over $100, our cost would be reduced dramatically. Currently, the track is planar. We will implement a 17-degree slope to and from each station to make the track more realistic. This feature might prove to be a challenge. We will need to work with the bogie team to make sure the bogie can traverse the slope. Implementing a slope will most likely cause the cost of pieces as well as the difficulty of manufacturing the pieces. Creating a modular track requires consistent length pieces. We will adopt the previous measurements by designing sections in multiples of 250 millimeter lengths as shown in this drawing. This will make the track expandable and configurable. We will also experiment with a bank angle for the curves, although this might not be necessary and could create problems. This is a version of the proposed track created by the summer team. We will be able to expand upon this design to allow for more bogies and at least 8 stations. We will be able to fill in the gaps with multiples of single modules as shown between the double track. After we meet with Scott Bryant from Vanderbend, we should have an estimated budget. We are looking forward to a more realistic Superway network. And now the cabin and bogie team.
I'm just going to talk briefly about the cabin and bogie. First of all, since we are the small scale, our cabin and bogie is kind of like a research and development section for the intermediate and full scale. Because if we mess up, it'll fall off the track. You know, it's not so much of a big deal, but if you're full scale falling off the track, we're going to have a big problem, right? So this is currently what our bogie looks like. It's basically the drive for our entire project. You see it has the motors and this, at the bottom there's kind of there's a servo, and that's what's controlling our turning mechanism, and we're going to talk a little bit more about that later. But for now, this is our cabin. It just houses our Arduino, has some ultrasonic sensors that we don't have on there right now, and we're not entirely sure if we're going to use them yet, but this is what we had from the previous teams. So one of the really big problems we have with the cabin is that there's just too many components. You can kind of see that on the cabin there's pieces of metal. It's like 4 or 5 pieces of metal put together, and then we have a bunch of screws on there. And this is a problem because we took this out to De Anza for display, and unfortunately we did drop the bogie. It was an accident, but what would happen is all the screws came out, and since there's so many screws and so many parts, you have to put them all, tighten them back all together so then it's not all wobbly. But some of them you just couldn't get to with the tools that we had on hand because there's so many components. So what we want to do is kind of make the structure
like a solid piece, maybe get a sheet metal or something, bend it, drill some holes through it, and that way we have specific areas where we're going to put screws through, and it's not going to be rigidity, I guess. And then another problem here, it's not really a big problem, it's more of a aesthetics kind of thing. Clearly you can see that our cabin looks nothing like any cabin at all, right? So what we're planning to do, maybe 3D print something similar to what the Swedish design for the cabin is. This will help us because at De Anza, when they were looking at it, all the people came over, they understood that it was some sort of small scale model, but they didn't really understand what it was. So if we put something that looks more like resembling the large scale cabin, they'll get a better understanding of what it would be. And I'm just going to pass it off to Brian.
So on the left hand side, you can see this is Bogey designed by the summer team. So if you focus on the servo, the switching mechanism is operated by the servo and 2 piano strings. The problem is the piano string is not stable enough and is loosened. So when we want to switch from right hand side to left hand side, the piano string will not respond like instantly. So and we want the Bogey design to be look alike to the full scale one, like on the right. So we have to do some modification or redesign to the Bogey. So this one is one design for the switching mechanism. So it's also operated by the servo, but it will be a more solid piece, so that and it's directly connected to the servo, so it will respond like when your servos turn, rotate, and then the mechanism will just respond immediately.
So I'll be talking about the controls. Currently, Bogey does not have any control system. You just push on and off, it goes on. And they have magnets to locate the stations if something doesn't work, and then the Bogey goes around like a couple rounds before it goes to the station. So we're trying to bring up a position system into the Bogeys. We have 2 options. One is GPS, one is IPS. Does anybody know the difference? Alright, so GPS is the global position system and the IPS is indoor. GPS is good for outdoor application. It gives you better accuracy. You can use it worldwide. Satellites are used for this purpose. And IPS, GPS not that much good for indoor. Basically, buildings have insulation that blocks the satellite signals, and then we don't have quite good accuracy. The accuracy is off by like 10 meters in GPS, and our Bogey system is not that big to compromise that. So we're going to create an IPS system, indoor position system, that can locate the position of the Bogey along this track. So what are our options right now in the market? If you look at it, we have infrared, radio frequency, and ultrasound. Infrared and ultrasound have drawbacks. You need to have a straight focused line, length, and then cameras for infrared. So we're going to go with the radio frequency, and more specifically with the fingerprinting of Wi-Fi. So how does it work? Basically, the different approaches that we have right now is going to be Wi-Fi and beacons. So the Wi-Fi is going to transmit Wi-Fi is going to receive the signal from the beacons way along this track, and then from that point we're going to map it up onto the computer system and then see exactly the position of the Bogey is. So how does the Wi-Fi system work? So the Bogey, we have a small chip, it's called Wi-Fi chip, also called transporters. It will transmit a signal, and then one of the Wi-Fi signals along the station pad is going to take the signal and then send it to the computer. From that point on, we're going to go back, do a calculation, and see exactly where the pinpoint and position of the Bogey is. They have 3 main components, not that many. We have tags on the Bogeys, we have readers or transceivers on the stations, and then we have a computer system that can basically take the data and then compute it and give the signal position. Before we can do any of those things, we need to localize the map. We need to have an exact map of the track on the computer program that can show us pinpoint where exactly the Bogey is. There are many many companies that have this cool gadget that makes you create your own mapping. but it costs a bit of money, so we're just trying to work it out with those people right now. And then I've sent the email. They're waiting for a response yet. That's about for the system. And we have a Thomas Newman going to talk about the communication.
So based on the team over the summer's design of the communication between the pods and the main hub, there wasn't really any form of like multiple pods interacting with the main hub. At least we tried working it out, but in terms of like the Korean team's code, it wasn't. We didn't really see it too well. So there was a. So we kind of asked ourselves, like, what should we do in terms of improving the communications? So currently the system's using XVs to communicate between the pod and the main hub, but we also were looking into the Wi-Fi shields that Arduino currently has. So why were XVs used originally? Well, they're a lot easier to use, they're very simple, and the current rating at 3.3 volts is very minimal, well, for the most part. And it's based on a radio frequency sort of kind of communication. They have a structure seen as on the picture to the left. It's a coordinator, router, and an endpoints where the main hub will communicate to the routers, and the routers will relay the messages to the endpoints, which is the bogies. While that structure is great and all, it's XVs are meant for more simplistic kind of forms of communication. So if we wanted to make the system more sophisticated, we were planning on using the Wi-Fi shields for communication. This Wi-Fi shield in specific is the CC3000. It's used for a lot of home automation and other small-scale BRT projects. So with Wi-Fi, the data transfer rate's a lot faster, more reliable. Plus, in terms of the current rating for these, they're not so much more in comparison to the XVs at 3.3 volts, of course. And yeah, so that's why we're planning on using the Wi-Fi shield. So I'll take it to Kenny for the collision detection.
Okay, so one of the goals of our small scale is to implement more carts that are individually controlled. And in doing so, we ultimately have carts going at different speeds, stopping, going, etc. So one of the things that we want to develop is a system that essentially prevents any collisions from happening between the carts. So when doing a little bit of research about technology that's being developed as of right now, I came across the adaptive cruise control concept, which is being implemented in some cars. So basically how it works, it has ultrasonic sensors attached to the front bumper, which sends out a high frequency sound wave. And what happens is if there's an object in front of it, the sound wave bounces back and is received by the unit on the car. And then from there, the mechanism either usually decelerates the car accordingly. So I saw a couple videos, including demonstrations on this, and one of the things that the driver noted is that he didn't want to take his foot off the brake. He found that the cruise control was stopping a little bit too close to comfort from the other objects. So it's definitely something that we wanted to improve on. So first, this is just an example of one of the modules that we might use for the Arduino if we do decide to use ultrasonic sensors. However, we also came across infrared sensors as shown here. And so it's essentially the same concept except that it uses a solid state laser instead of a sound wave. And what we found was that it's a little bit more accurate because there's less interference between a sound wave versus a solid state laser. Okay, so in terms of challenges that the control team might experience, definitely one thing that we noticed is that we're going to have a lot of different components with a lot of different systems. So one thing we need to make sure is that there's not going to be interference between the signals that we're sending out. And also, due to the fact that we're having all these different types of sensors and whatnot, our program has ultimately become more complex. So we just need to make sure that we are able to debug and make sure everything runs pretty smoothly in time.
One more thing I would like to add is this new system that I'm developing right now is called track IDing, and it's meant to be used as perhaps a location system or knowing where the cart is in terms of what piece of track it's on. So as you can see, this is the barcode right here, and on each piece of track, the barcode's like at the beginning of that section. So that way, when our carts run through it, it scans the barcode and knows what ID it has. That's sent back to the control hub, which processes all that information. And the way this works is by having a foil here. We have a high intensity signal coming from the light sensor, which then signals it to start recording. And from that, we have a unit length which is timed, and you figure out where like the sensor needs to like take inputs from each of the sections of the barcode. So here's a prototype I did with it. I didn't have a laser or anything, so I used an LED and tried to condense the light into one point. And here's the light sensor. They had to be put in an angle and stuff. Up there are the early barcodes I developed, or I made. It's pretty much just a piece of foil with Sharpie drawing boxes. Here are early tests I've done. On the left, you could see that it read 101 and a bunch of zeros after that, and then for second reading, it only missed one of the sections of this first piece of barcode, and it's that last one right there, or the last bright part. It might have been timed off or something, because that bar is actually quite smaller than the rest of it. So this is one of the things I'm trying to develop, so that way we have an idea of, in case the positioning system does not work, this is a second option, and also this could be used in place of the Hall effect sensors, which require magnets on each part of the track. So this is like a cheaper option, we do go with it. Here's a project timeline, or an Gantt chart of what we have done and where we're at. This line represents today. This is everything we need to do, and that's everything that's already been done. So that's the end of our presentation. Do you guys have any questions?
So, Najra, you mentioned that the Bogey does not have a control system.
Positioning system. Sorry.
There were some Korean students, electrical engineering students that worked all summer.
They did. They did make a map,
system.
and then they did have stuff.
So I don't understand what you were trying to say.
Sorry, it just meant the position system, like exactly to pinpoint the location of the boogie along the track.
I see. Okay. So now I don't understand. Are you going to use the system that you're talking about, a barcode along the side of the track to know where you are? I didn't understand why you're going away from XB to Wi-Fi, and the beacons. What kind of resolution is that going to give you on the?
Beacon's going to give us the Wi-Fi and the beacons together. Going to give it resolution of 5 to 10 centimeters.
5 to 10 centimeters.
Beyond along the track, so it will give you the exact pinpoint with the accuracy of 5 to 10 centimeters. Right now, the XB is hard to control. It's a Bluetooth Wi-Fi. I mean, like Bluetooth signals, and it's not consistent.
Also, with the XB system or XB chips, instead of using XB, we're trying to use a Wi-Fi system, so that way we have one central communication system between the computer, the cards, and also like potentially the app that we want like implement onto the system. So that will increase our expandability. If we want to use an app like that uses Wi-Fi and needs to connect to our server, then we would have to have that Wi-Fi system anyways, and then we would have to also have the XB communication system with the cards. Instead of doing that, we just have like one central thing that control everything.
I think with the XB network, you can have like 128 or some number of different nodes in the network.
Yeah, but XBs only communicate at around like 200 kilobytes per second.
What do you need?
Well, if we have something that this big, we could expand it further and further and not be limited by the XB. Also, the cost is about the same, so there's not much difference between that. And as Thomas mentioned earlier, the power consumption in terms of amps, it only consumes about 50 milliamps more than the XB at 3.3 volts. But so it's not that much off from the XB, but it will be more flexible with our system or with the small scale. Anyway, yeah.
Yeah, I just had a question for the guys doing the track team, which is why are you guys doing a sloped track when pretty much the entire goal of the quarter scale is to show that slope and have a suspension system for it as well? I was just, I thought the main goal for you guys was to kind of show like a city layout and how it would move from the location to location and not necessarily have it go down. That's pretty much the whole point of the scale.
We haven't finalized a station design. We're just looking into the possibility of, we'll talk to Vanderbilt also and see how realistic it is budget-wise and manufacturing-wise, but yeah, and then we need to coordinate with work with the Bogey team to make sure that it's possible, but I think it would just be more realistic and it would add to the track. So if we could get it working, it would just enhance
Okay, well, I was just making sure because I don't want you guys working so much to get that track to go down when the quarter scales can be working on themselves to show that.
Right, so we might even have a various amount of station designs. We will definitely keep one of the stations the same as it currently is. We've also looked into, Henry also came up with another idea of a station design.
It's connected to driver now?
We should move on because we've got one more group and then Steve is here to talk to you guys.
Just some very quick observations. You guys are talking about a lot of things which are computationally expensive, and Arduino is not a very powerful thing. If you were to implement 2 different location systems and Wi-Fi and everything that you're trying to do, a single Arduino cannot handle it. It just can't. So as you're coming up with these algorithms, pay very close attention to the computational expense of each of your algorithms and how they fit together and however many systems you need to talk together.